All right, guys, so we're moving on, talking about density curves and then the normal distribution. That's a pretty common term that I think you've heard of a normal distribution before. We're going to look at what that actually means today. So when we're doing these density curves or a normal distribution, we talk a lot about location of things, quartiles a little bit, and percentiles a lot. Like, you know, when you get results back from a score and from a test and you see like, oh, I'm in the 89th percentile. Like, we're going to look at where that comes from, like how that information is determined. Okay. So if we're talking about quartiles, the easiest thing to think about is a box plot. So with that, think box plot. Where is, like if I asked you for Q1, draw you a little box plot up here. So on the box plot, guys, where is the Q1 value? There we go. Yeah, go ahead.
It's the lines coming out of the box, like attaches to the actual box.
So like the edge of the box? Yes. Yeah, this first one right here. This is where Q1 is. I'm sorry, I'm squeezing that in. Does anybody know what percentile that corresponds to?
25.
Yeah, that's the 25th percentile. Remember with a box plot, each whisker, those are the lines on the end, each of those contain 25% of your data, and then each half of the box contains 25% of your data values. So Q1 corresponds with the 25th percentile. And then talking about percentiles, like what that means, let's say you were told you're in the 90th percentile. What that means is that 90% of the scores are below your score. And it can be phrased in different ways. 90th percentile, sometimes you'll hear you're in the top 10%. Okay, that corresponds to 90th percentile. Being in the 10th percentile is very different than the top 10%. Okay, so just make sure you read the questions carefully and you can see exactly what we're talking about. And this little part here, if we don't have the complete list of data, how can we estimate how an individual ranks? What we're going to look at is if we're given their score and the mean and standard deviation of all the scores, how do they rank against everybody else? We'll look at, I have an example here with an SAT score and an ACT score, you know, which one did they actually do better on? You can't just compare the two scores as it is. So that's kind of what we're going to get into today. So density curves. These are for continuous random variables. So for a continuous random variable. So we are going from a histogram to a curve. I'll draw you a little histogram here. So that's a histogram. That's what we were talking about in last unit. When we're talking about a continuous random variable, you're not going to see these like separations the way you do in a histogram, like the different kind of chunks. It's just going to be this curve that can follow a similar shape, but that's what we're talking about with a density curve. So a lot of the same ideas that we had with histograms, but now we're going to look at them in curves. And as far as description here, it just shows us like the nice overall pattern. Okay, you can see we had these bars essentially in our histogram, and now we can just see this nice smooth continuous pattern that's going on. Okay. All right, some properties of our density curve here. If we have areas between two values, so like two different ACT scores, the area in between that, it represents the proportion of observations that fall in that interval. So you guys in calculus, you've learned about area under the curve. Going to talk about that a little bit. You don't have to know any calculus to do this, okay? So don't get scared. All right, so it's the proportion of observations that fall in that interval. If we wanted to talk about total area under the curve, so not just in between two values, but the entire curve, you know, you've got a little distribution, the entire thing, if we were talking about everything under there, that area is equal to 1. That's because that's where 100% of the values would be, okay? All right, your curve is never going to cross the x-axis. You can see on the couple that I've drawn it where the tail's ends are approaching the x-axis, but they're never going to cross it. So curve never crosses the x-axis. The next one's a little weird. The height of the curve, it doesn't mean much, okay? It doesn't really tell you anything. Doesn't tell you much. We'll care about like where the maximum occurs, but you don't care how high up it goes. It doesn't really mean anything, okay? All right, and then an area under a single point is 0. Kind of a throwback to your geometry days. We thought about points, lines, and planes.
choose their tests. I'm checking.
Oh, they didn't give you. Here, grab one of these packets. Right here. Okay. Thanks. All right, so we've got some different types of density curves. These are the ones you're going to work with this year. So the first one is the standard normal curve, and that's the only one we're actually going to do much with right away. It's sometimes called a z-distribution. You've seen them before. We've already drawn a few of them. Tail doesn't really curve up like I did that. Hopefully you can draw better than I can. Your mean equals your median with this because it is a nice symmetric distribution. All right, then we also have the t-distribution. So the t-distribution is really similar to the normal curve, but it has something called degrees of freedom. It's got a little more spread. We'll talk about the tails being fatter, and that's something we'll use a lot more later in the year. So we'll say similar to the normal curve. With more spread. Has degrees of freedom, which is fine that you don't know what that is yet. We'll get there. And fatter tails. And again, guys, if you ever can't read anything I'm writing, let me know. I know, especially in the back, it's not always easy to see. Yeah. Yeah. Kind of listing different thoughts for you there. And then the last one is the chi-square distribution. It's skewed right. And I'll draw a picture for you. Again, this one we won't use for a while, but these are just different examples of density curves. So that's what a chi-square distribution looks like. You can tell it's definitely not a normal curve. Okay, so the one we're going to focus on right now is the standard normal curve. So we've got some properties. Bell shapes, that's what we've been drawing, that shape you see. Like if you hear about, oh, there's a bell curve to how scores were distributed, that's talking about the normal distribution, okay? And this n0, 1, what that means is when we standardize, the mean is 0 and your standard deviation is 1. So the reason it's a capital N and then 0,1, that's representing the normal curve. So the standard normal curve always has a mean of 0 and a sigma of 1. Because it is perfectly symmetric, your mean, median, and mode are all going to be the exact same thing. We're not going to talk about inflection points on it, sorry guys. But the last one, the empirical rule, this is pretty important. The 68, 95, 99.7 rule. Okay, that's called the empirical rule. You turn the page here, we'll draw that out on an example for you. So any questions before we turn the page? Okay. Okay, so we have this lovely standard normal distribution picture for you. We're going to fill in some percentages, and then we're going to put the IQ distribution on here as well. So first, the empirical rule down here at the bottom, this 68, 95, 99.7. What that is talking about, there is the mean in the center. If I draw one standard deviation away, above or below, that's going to contain 68% of the values. So 34% here, 34% here. So that's if I'm one standard deviation away. So write the rule at the top for you since it's on the previous page. That's your empirical rule, 68, 95, 99. If I go 2 standard deviations away, really, it should probably be out a little more, but that's okay. That will contain 95% of my values. So we need to figure out, 68 one is easy, right? I just split it between these two. Now including the 68 and then these two, that's how I get my 95 total. Okay, so what are each of those going to contain? What percentage? What did you say, sir?
13.5.
Yeah, 13.5%, good. And I know it's hard to squeeze it in there. Okay, and then according to the empirical rule, if I go 3 standard deviations away, above and below, that will cover 99.7% of my values. So what is going to be in each of those little sections? What do you think, guys? Yeah. Well, 2.35, I would say, but yeah. So that's 2.35%. Does that make sense to you guys where those numbers are coming from? Okay. What does that leave for beyond 3 standard deviations away? How much will be on each side there? So 0.3 between both sides, so how much on each side? Yeah, 0.15 in there. 0.15%, so a very small amount. You can certainly memorize the numbers from what we just filled in, or hopefully if you just know those 3 numbers, you could fill those in if you needed to, okay? Questions on those? I know that's just a lot of numbers. Give you guys a second. If you can't read something again, let me know. All right, so the next part, it says that IQs are normally distributed with a mean of 100 and a standard deviation of 15. So they're asking us to use the picture above to show the distribution of IQ scores. So the mean is 100, so that's easy. That goes right in the middle. And then the standard deviation is 15. So if you were one standard deviation above the mean, what would your score be? 115. Good. What about 2 above? 130, and 3 standard deviations above? Yep. And then the opposite way, if you were 1 standard deviation below, 85, 2 standard deviations below, 70 left, and then 3 standard deviations below, 55. I think we add better than we subtract, maybe. Okay, so you might be asked to just show these scores that are distributed normally on a distribution. That's it. All right, so then we can answer questions about this. Based solely on the empirical rule, approximate what % of individuals have an IQ lower than Forrest Gump? His IQ was 70. So what do you think? What % have an IQ below 70? Yeah, that's
2.5.
good, 2.5. You just look where 70 is and then total up the percentages below that. So that would be 2.5%. And then the next part there, again with the empirical rule, looking at our little display here, approximate what % of individuals have an IQ between 100 and 130. Yeah. Yep, good. 47.5%. Okay. So that's how you can use the empirical rule. You're going to learn how to do all of this on your calculator where you can put in exact values. But if you're given scores that fall nicely on the standard deviations, you can always use the empirical rule. It's a little tougher if I said, well, what % had a score above 132? Okay, you're going to be a little off if you use from 130 and up, right? So we'll look at how you can do that on your calculator. All right, so we're going to talk about the mean and the standard deviation of your normal distribution. So if it is a normal distribution, the mean, remember which is mu, is always the peak of the normal curve. All right, and then standard deviation. Remember, standard deviation tells us about how spread out your distribution is. So the larger sigma, the wider the spread. Okay, so the bigger your standard deviation, the wider the spread. And that's of the normal curve. Okay, so now I've given you these pictures. Can you guys see the three curves? Like A is this first one. B is this like short line one, and then C is the last one. Okay. I want you to try to answer these two questions for me. Try it on your own. Talk to your neighbor, see if you guys agree, and then we'll go through them. So order the curves from largest mean to smallest mean, and then from largest standard deviation to smallest standard deviation. Okay, so try to put them in order, A, B, C, and then talk to each other about it too. I'm going to take attendance.
I agree with you on the second one. One like the largest mean.
Oh. This is what we're going to do. I was thinking what the tallest, what numbers they get that way.
Sounds like
Maybe a later.
It's a good debate.
yeah. I've had one. Yeah, it makes sense.
Yeah, that's true. That's true.
All right, guys, let's see what our consensus is. So, guys, put your phones away. Thank you. All right, so I think the second one is easier to answer than the first one. So the second one, standard deviation. What do you think? Largest standard deviation to smallest? Yeah, go ahead. B, C, A, yes. That's easy to see. It's just how spread out it is. Now, the first one, the largest mean to smallest mean. A little trickier. Yeah, what do you think? I have a vote for CBA. Agree? Okay. I see some hands not up, so what's your other thought? Or are we just like, I'm not voting? Ethan? What'd you say? ACB, okay. So you went with heights, right? Which is an easy thing to do. You normally are like, oh, well, that's up higher. That must have the biggest mean. Do you remember back here when I told you that the height of the curve doesn't really tell you anything? I know. It doesn't. It's weird because you're looking at it, you're like, that should be higher. But it's like you're looking at this number line. So that's where A's mean is, B is somewhere in there, and then C's is over here. Okay, so you're looking just basically with like a number line, which one's further. So you're not alone, okay? Heard plenty of people saying in that order. So the correct answer is C, B, A. Okay, so good job, guys, to figure that out. All right, any questions on that? Let's keep going. All right, so identifying the normal distribution. What this is talking about is we're going to have conditions that we have to check. So, condition to check. When we start going through some of our bigger problems, you'll have different things to check. One that's very common that you have to check is normality. Like, does this follow a normal distribution? So there are a few different ways that you can check that condition. Condition to check, sorry. First, it might just be given to you in the problem. You'll be reading the problem and it'll say, and the values were normally distributed. Great, that's the easiest one. We like those a lot. Given makes us happy. Sometimes they will just give you all of the data values. If that's the case, then you have to do a little bit more work. You could create a histogram or a box plot and look to see, does it look like a normal distribution? If that's the method that you choose, you have to include a sketch. So must include sketch. The second way when you're given the data is to actually check for the empirical rule, like to look and see what percentage of the values fall within 1 standard deviation, 2 standard deviations, and 3 standard deviations. No one really ever does it that way. So it's an option, but it's kind of tedious to look through, and it's just not really commonly used. The one that we use most often, if you're given data, is the normal probability plot. Okay, so that is on your calculator. We're going to go through that in this example down here, but I would say this is a nice one to use. So this is on your calculator. So go ahead, grab your calculator. We'll just go ahead and put in these 20 student values below, and then we'll go back up and check. Don't have your calculator, look on with someone else. All right, so we're going to put these values in. Do you guys remember how to do that? I see some of you are already doing it, so clearly you remember. We're going to Stat, Edit, and I'm going to put mine in List 1. All right, so once we have our values in there, does anybody need more time? Okay. You're going to push second y equals so we can get into that stat plot again. So second y equals. And then push enter. Make sure it says on. Mine says off, so I need to highlight on. And then type, we have to pick the normal probability plot. So that is the last option here on your graph. So the way you get there, just keep arrowing to the right, and it'll take you there. So you want that last one highlighted, and then push enter. Your data list, mine says L1. That's where I put my data, so that's what I want. Just leave the data axis as your x-axis and mark it's whatever you would like to see them show up as. I always leave that first one. I'm not going to just push graph though. I'm going to, from here, push zoom and then 9. So zoom is right in the middle at the top. Zoom 9 is the one that says zoom stat. So push number 9. And then that is what your graph should look like. So let me walk around and see who needs. Good. Go. Okay, you have one at home? Yeah. Okay. Troubles? You're like, oh, zoom. Top middle, and then 9. Right. Okay. Oh, your space. So, probably the sense. Right? See all these like weird. You just don't want to figure all of those. Oh, there you go. Get it? I see your phone. Okay, finally we got it. Okay, guys. All right, so we made this normal probability plot, but you know, what are we doing with it? So what you're looking for when you make one of these is to see, is it fairly straight? Like, does it look like a fairly linear plot? What do you guys think? Does it look pretty much linear? Yeah, it does. If it's not, you're going to see like a big curve or like an exponential growth type of graph or a log graph, things like that. You'll see some sort of other strange pattern happening. But if it is roughly normal data, you're going to see a fairly straight line. Remember, nothing's perfect. Like, it's not going to be a perfectly straight line or a perfect distribution. This is definitely close enough. Okay? So that's what you're looking for. So make note of that. Whoops, too many things going. There we go. So you are looking for a fairly straight line. All right, so that was all if you're given a set of data values and you're checking the normal condition. If you're given a graph, you have to check. I guess I see that. They're doing some sort of experiment. All right. If you're actually given a graph, then you can just look at the shape right away and say, oh yeah, that appears approximately normal. And if you're given that shape, that's easy. You can just look at it and say it's normal, or nope, that doesn't really look like it's normal. All right, so let's go back to our data values here that we already put in. That's weird. All right, are these guesses approximately normally distributed? So we already did our normal probability plot with these. That's the evidence to support your answer. So you're going to say, yes, they appear approximately normal because our normal probability plot was fairly straight. Okay, so these guesses are approximately normally distributed. Normal probability plot shows a fairly straight line. All right, does that make sense how you check that? It's not too bad, right? Okay, so now we're going to move on to the z-score part of this and how you actually use the normal curve and make comparisons to different things. So a standardized z-score, first thing here, caution what we're putting there, just don't assume your data is normal. Not every data set you're going to get is going to be normally distributed. So don't assume data is normal. You always want to check. If you have a data set that, you know, is strongly skewed right, but yet you apply the normal distribution to it, it's not going to work because those characteristics are not going to match up with the data that you have. So the way you find a z-score, the common equation here is statistic minus parameter divided by standard deviation of statistic. So that sounds very confusing, but when you use it in a problem, it's very simple. This right here is the much more formal formula. You can see it's slightly different than this z-score formula. Right now, our n is 1. So we can use the common equation. So the mu and sigma, those are from the data set that you're looking at, and then the x is whatever your score is if you want to figure out what your z-score is, okay? And then what the z-score is telling you, what it measures, is your location. It's how something compares to all the other values in the set. And again, you can use these z-scores to compare different individuals, but only from different normal distributions. You can't get a z-score for someone with a not normal distribution. It doesn't work, so you can't make those comparisons then. Okay, so let's try one. So if we're ready, go ahead and turn the page. All right, so we have Mike. He wants to figure out which score to send up. He's got his SAT score and his ACT score, and he wants to basically know which one is better. Okay, and I tell you, so this N 1500 250, that is the mu and sigma from the normal distribution for SAT scores, and then N 216 mu and sigma for ACT scores. Okay. We got to figure out which one he should send. So I'm going to find the z-score for the SAT. And the ACT. There's kind of room on either side here. And I can go right to finding the z-scores because they told me that they're normally distributed values. That capital N with the 1500 and 250. That's saying, hey, this is a normal distribution, so you can just go ahead and find the z-score. So the way you find the z-score, we had that formula. So we're going to take Mike's score, which was 1700, minus the mu, which was 1500, over the sigma, which was 250. Now you could write divided by the square root of n, but that's not going to change the value of this at all. Okay. So what is his z-score for the SAT? What do we think? What'd you say, Ryan? Yes. And what did you get for your decimal? Just if you, yeah, there we go, 0.8. So his z-score for the SAT is 0.8. So we want to find his ACT z-score so we can make our comparison. So again, you're going to do Mike's score, which was a 24, minus mu of 21. Yeah. What did you say, 0.5? Yes, good. Divided by 6, so that z-score is 0.5. Okay, so just to clarify, the 0.8 and the 0.5, that's not like 80th percentile and 50th percentile. That's not what it means. It's just the location on the normal distribution. Let me draw for you. When you have standardized your scores and we're looking at just a normal distribution, that center is always 0. Okay? So if you have a positive z-score, it's to the right of 0. It's above the mean. Okay? If you have a negative z-score, you're below the mean. If you have a 1 for your z-score, that's 1 standard deviation away from the mean. Okay, so we've got 0.8 and 0.5, so neither of these are super far away from the mean, but the 0.8 would be further above the mean than the 0.5. Okay, but again, it's not connected to percentile when you're looking at z-score. Just want to make sure we understand that. So he should send his SAT score. Do you guys have questions on that? Okay, do you need a break here for a second? Yes, I feel like it's always so much writing on the first day of notes. So guys, let's just take, I don't know, 5 minutes. Please. Take a minute, okay? Are you dying, Gabby?
I like all this stuff. In my life.
I think it's worse in my 7th and 8th, but yeah, I think by the end of the day, you guys are. Do you guys find Red Day longer than Black Day?
I have I have like all my APs today.
Oh, okay. Yep.
Like yesterday I had like English and math.
Okay. Easier day. I know. Math at the end is rough. It definitely is.
I had first grade last year in my house.
Well, yes. So we can only have math in the middle of the day.
Because I just have to lunch because it was
It's hard, I know. It's also hard the first day of a unit. I know I just spew so much information at you, so we got to get it out there so then we can do something with it. So.
Where is it?
Are they like cracking down out there?
Wait, are you outside?
Yes. We'll start here in just a couple minutes, okay? All right, we'll wait for it.
What's that? Yeah. That's good recipe. I'll be there. And what? That's great. I agree.
And it's not even involved, but you get better. Oh, no,
Just this is cool.
and this is like, oh, like the ice cream.
I think we actually like lost touch with our subscription, so we can't watch film. I can't watch film. Yeah, we forgot the cake. So basically, we lost film. Probably not to the cake one, so we don't have it.
Yeah, but you can.
Yeah. And you did about it recently.
You what?
Yeah.
I got better things to do than watch that film. I got better things to do than watch that film.
And her bathroom No, I know that's why.
I keep looking at my
No, I
like missing.
No, I know, but like she's not the type to just like get it, like not come back. Like she's not.
Okay.
So like we we're like out in the bathroom and like I came out and everybody was like, where's her? Like I don't know. I already texted her like while we were doing it. Like I texted her, I was like, wait, but then I forgot her phone.
Yeah.
So
Okay.
yeah.
I'm sure to follow up.
Yeah. Yeah. But yeah, no, but she's not the type.
That's good.
So it's not like she's just like making circles.
Right. She's not the kid who just wanders.
Yeah, exactly.
Like,
I think like something's
okay.
I know like her car got hit, like I came out like yesterday and then like her phone broke and like her mom was out of the whole thing. So she's just like I think it just happened a lot. Yeah.
Okay. Oh, goodness. Well, thank you.
Yeah.
All right, guys. 25 minutes left. Okay, we can do this.
Imagine if you do that like you do that parking lot zero
All right, guys. So let's look. We're now trying to figure out percentile ranks for Mike here. So the first one says, what percentile does Mike rank for his SAT score in the previous example? So there's a couple ways you can go about doing this. We're doing both of them on our calculator. But you can do it based off his standardized score, which we found his z-score, or you could just use his original SAT score. So I'm going to show you how to do that both ways. So always make a picture when you're doing these because it makes it so much simpler to see what you're looking for. So if I'm looking at the standardized score, meaning the standard normal distribution, 0 is the mean, and he had a z-score of 0.8, so I know he was somewhere above the mean, right? 0.8 would be somewhere to the right. So as far as percentile ranks, we know he should be above the 50th percentile, right? Because he's somewhere to the right. So I'm trying to figure out, like, what is this area up to that 0.8, okay? So you're going to use your calculator. You're going to use what's called normal CDF. So normal CDF stands for normal cumulative density function. It's cumulative because we're going right up until this 0.8. So let me pull up my calculator again for you. Okay, this is in the distribution menu. So you have to push second and then vars. As you can see above that, it says distribution menu, okay? So second vars is how I got here. Anybody not finding it? Just ask if you like miss a step ever on calculator stuff. Don't be shy. Second vars is how I got here. Okay. I'm picking normal CDF. That's not the first one, it's the second one. We want the cumulative density function, so I pick 2. All right. Lower, it has -1 to the 99. That's basically saying negative infinity. Okay, so that's really far to the left. And then the upper is what we're coming up to, which was his z-score of 0.8. And I'll show you on my picture here in just a minute. And I'm using the z-score, which means I want the mu of 0 and I want the sigma of 1. Okay, like this is all with the standardized values. Okay, so then push enter and push enter. And hopefully you get 0.7888. Yeah, exactly. Anybody not getting that or stuck? Yeah.
You found up
Okay, so you're going to do like negative. So the older TIs don't prompt you for the information, you have to just know which order it goes in. Okay. You know. Yeah. Everybody good? Stuck anywhere? All right, so that is telling you his percentile, so he is right around the 79th percentile, okay? Right for you, so we did basically negative infinity to 0.8, and we did 0 to 1. And we got Mike ranks at about the 79th percentile, okay?
For these three responses, do we need to like write it out to be specific like we did last unit? Or
Yeah, when we get to like what the free response questions look like, you'll see that there's some detail you have to put in there as well, of course. And you want to label like the calculator. They don't like just calculator speak, okay? You want to label things like this is mu and this is sigma. Like those two you definitely want to label.
You just answered.
Perfect. Now, let me show you how we could do this if we didn't already find his z-score. You don't have to take the time to find it. We could draw another picture and just base it off of the original SAT information. So the SATs are normally distributed with a mean of 1,500, so that's where the mean is. And he scored a 1,700. So again, I'm shading, like I want the area of the curve, under the curve, up to his score. So again, you can see how it's negative infinity, but this time it'll be up to 1,700. So let me pull up my calculator again. So we're going to go through a very similar process here. You're going to do second bars again. And you'll pick normal CDF. But now instead of 0.8, you're going to put in his score, which was 1,700. And then the mu and sigma from the original distribution. So that was 1,500 and what, 250, I think? Enter. You should get the exact same thing you got with the last one, okay? So it's whichever one you kind of started down a path on. If you had to find the z-score in some other part of the problem, maybe you want to do the z-score way. A lot of times you're not going to find the z-score then, and so it's easier to just use the values you're given. Okay? Anybody questions on normal CDF? All right, so I want you guys to try the next one. What percent of individuals scored higher than Mike on his ACT in the previous example? So make a little sketch. And I don't care if you use his Z-score or his original score, it should work either way.
That's what percent that higher.
Check with each other if you haven't already. What percentage scored above him? What do you guys think? What'd you guys come up with? About 31%? Yeah. Okay, and there's a couple ways you can do it. Did you guys do it just like we did on the last one and then subtract? Okay, did you go from that score up? Okay. All right, that works. I would go, and I'm going to do it with just the ACT scores, not the Z-score. So I'm going to say from 24 to infinity this time, and then the mean was 21, the sigma I think was 6. There are multiple ways you can get to this answer though, but we end up with about 31% of ACT test takers. How do you do what? I'm sorry. So I think the ease is just like 9,900. I know that's not infinity, but that's a large enough number compared to everything else that you're doing to show that that's really far to the right. So you can do like with the exponents too if you want to. Questions on that one? I'll show you on the calculator. If you were like, oh, I don't know, I don't know how to change this. I'd like to leave that alone. You could go, okay, up to 24, new mean and standard deviation. And you get an answer. And then it's just, you know, subtract it from 1. Ooh, I got a different answer. What did I type in wrong?
66.
Ah, that'll do it. Yep. Thanks. That's a dramatic standard deviation. Let's try. There we go. Try again. Okay, much better. And I know I'm going to get the negative here, but that's another way you can do it if you just wanted to use what was already put into your calculator. Or you could go from 24 to a really large number and you get there. Okay? We doing all right with these so far? Okay. All right, try the next one. So what % of test takers score between 23 and 27 on their ACT? You guys get in the habit of making little sketches, drawing pictures. It's a crucial part of answering a lot of your AP questions. So I want to know who scored between a 23 and 27. That little area, okay? Yeah. Yeah, so from what was up above, I believe the mu was 21 and sigma was 6, I think. Yep. So, since we're talking about the ACT scores, not their C scores, you don't want to use the mu and 0 or the sigma 1. What do you think?
21 and 6.
Yes. Oh. Makes sense? Yeah.
Yeah.
Remember to put it in the ACT score?
So you're going from, so you would do 23, comma, 27, and then the mu of 21, sigma 6. Okay. All right, guys, so on this one, oh, no, you can come up here.
How do I get like the? How do I get like the lower limit after like -70?
Oh, okay, so it's like -1e to the 99th. Like if that's not there, you can just do like negative. But that's fine. What are you saying in this problem? What do you do?
Oh, I think for this problem it's.
Yeah. Yep.
Well, sorry, what did you say? Just negative and then
That'll work. It just needs to be something really far to the left if it's below her and really far to the right if it's further. All right, so on this one, we are looking in between values. So we're going from 23 to 27 with a mu of 21 and a standard deviation of 6, okay? And what did you guys come up with? Yeah, about 21%. So, yep, about 21% of test takers.
Will you always round to a whole percent?
You can, if you give me a decimal after, that's fine too. Yeah. Again, that's the weird part in here is there's no, it's like, oh yeah, you were close, that's good. It's very different. So they scored between 23, 27 on ACT. And do you guys see how I'm answering all of these with context? Like I don't just write 21% and that's it. Like, tell me what's happening. Get in the habit of writing that with the context, okay? Okay, let me pull up the calculator part. All right, so it's normal CDF again because we're finding like area in between those two numbers. Maybe. Now this time your lower and upper, it was between two scores. So your lower was the score of 23, while the upper was that score of 27. And then they told you the mean was 21 and the standard deviation is 6. Are you okay with that part? Okay. And then, oh, okay. I pushed enter a bunch. Is it working? Okay, awesome. Other questions on using the normal CDF? Yeah. So you don't have to. You can just use like negative, a really large number, just like type in a bunch of 9s and that'll work. You can do, let's see if I can get it up. Because what it was, the negative 1e to the 99th, like that's scientific notation for it, is all that's happening. So you can use an exponent if you want. But you just need a really large negative number, okay? Other questions, guys? All right, I think we're going to stop there because the next part we're switching gears into inverse norm, so we'll pause on that.
Yeah, it is today. It's